So let me start by introducing Jonathan Biteau. Today's talk, and first of all, welcome everyone to the next CDY-Initiative's seminar. Today's talk is by Professor Jonathan Biteau, and the talk is entitled Probing Extragalactic Magnetic and Radiation Fields with Gamma Rays. And we continue our series focusing on active galaxies and extragalactic sources. So Jonathan Biteau is an associate professor in the astroparticle group at the Irene Joliot-Curie Lab of Physics of the Two Infinities, Université Paris-Sud. Jonathan received his PhD from École Polytechnique LLR, and where he studied stochastic processes and gamma ray cosmology through spectral and temporal studies of active galaxies observed with HESS. Jonathan has been involved in several research directions in astroparticle physics and cosmology. He has been involved with the Pierre Auger collaboration, studying arrival directions of ultra-high energy cosmic rays. And he has been a member, actually, with regard to the Pierre Auger collaboration in 2018 for a period of 2 years. He led the Auger collaboration's arrival directions science working group. Jonathan has a long history in imaging atmospheric Cherenkov telescopes. He has been a member of HESS as well as Veritas collaborations. In fact, he was a postdoctoral scholar at UC Santa Cruz at the Santa Cruz Institute of Particle Physics. And I had an opportunity of working with Jonathan closely on Veritas. And he specialized there in variability of jetted AGN, study of interaction between gamma rays and the extragalactic background light. Jonathan is currently active in CTA. He led the CTA extragalactic science working group for a while, and he's also contributed actively to CTA instrumentation. He teaches. Jonathan has been teaching currently and in several topics in astroparticle physics using a chalkboard. So let us welcome Jonathan Biteau, and it's a great pleasure that you were able to give this talk. So please go ahead.
Thank you, Rashmi. It's an honor for me. So I'm going to try to share my desktop. Hopefully you can see it. And if that's the case, let me start. So I'm going to discuss extragalactic magnetic and radiation fields in voids mostly, and how we can probe them with gamma rays. I'll do also a brief aparté about fundamental physics, but that won't be the core of the talk. And I should start with a pretty picture. So this is not an actual picture. This is actually what you see on the left-hand side, the result of a simulation made by colleagues. What they did there is that they performed a constrained n-body simulation, and the constraints are such as they can reproduce the distribution of nearby galaxies to be more accurate the distribution of their peculiar velocities. So that's why you can see in this slice of 200 megaparsec width, the Milky Way in the center, the Virgo cluster north of it, the Centaurus cluster, both of which are part of the Laniakea supercluster, and in front of that, the Perseus-Pisces supercluster. What people are usually interested in when looking at such pictures are specifically clusters, filaments, sheets. What we are going to be interested in are voids, so typically 4 orders of magnitude less dense than clusters. And to give you an idea of the typical sizes that are involved in the system, I extracted here a plot from colleagues studying synchrotron emission from filaments. And they made a crystallographic model of the universe that I like because it's very simple. So consider that basically we are in a cubic face-centered system. The place where the atoms should be are the clusters. The edges of these cubes are the filaments. Each face is a sheet, like the local sheet in which we live in. And then the 2 typical sizes that are involved in such a system is the width of a filament, of an edge, and the size of a box that would be the size of the void. If you take 1 megaparsec for the width of a filament and 10 megaparsec for the size of the void, you end up with volume filling fractions that are roughly consistent with what is inferred nowadays with simulations. So most of the universe, 70 to 80%, is made of voids. We believe that there is a significant fraction of the baryons that are in the universe that are in there. And what we are going to study, or the way we are going to study them today, is with astroparticles. So to do that, we need to pick our particle gun. As all of you know, we have lots of them in the universe. Some of them live in our own galaxy, some of them in nearby dwarf galaxies, such as the small Magellanic Cloud and the large Magellanic Cloud. Those that will be of interest to us are going to be extragalactic, precisely because we can see how these particles are affected by their travel in voids. Gravitational waves, we don't care much about them here. They won't allow us to probe magnetic fields or photon fields in voids. But actually, there are two remaining ones that could be useful: TV gamma rays and ultra-energy cosmic rays. I'm going to focus the discussion today on TV gamma rays that interact with these orange photons that I will discuss more and can disappear. Note that actually these orange photons from the cosmic optical background and cosmic infrared background, they also affect ultra-energy cosmic ray propagation, mainly through photodissociation, so stripping nucleons from these nuclei. And we're going to use our favorite extragalactic sources, AGNs, but also long gamma ray bursts that we start seeing at TV images. The previous seminars that I've seen on YouTube, for most of them from this series, have focused on the objects themselves. What is the impact of the environment or the impact of the compact object in the center itself? What are the acceleration processes at play in such jets? The radiative processes, leptonic, hadronic, that generate the secondary gamma rays that we see. How cosmic rays possibly escape. This is a matter both for extragalactic charged cosmic rays and galactic ones. We are going to study today propagation, and mostly propagation on cosmic scales, so giga-year long travels, so as to probe these diffuse electromagnetic fields and fundamental physics. So here is a picture of how it goes. For once, it's actually a picture to scale. You'll see that we are talking here about logarithmic scales. And the central panel in there represents the propagation over, in this case, 1 gigaparsec. This is what is indicated in the bottom x-axis, from a specific type of source. So here we take, with Manuel Meyer, we take an AGN, and we take more specifically a blazar, that is an AGN with the jet that is oriented along the line of sight. And even more specifically, we take a flat spectrum radio quasar. And why do we say that? Because we actually locate here the emission region from which these gamma rays escape. So for FSRQs, we know typically that the gamma rays should come from something like a few parsec away from the black hole. And then a gamma ray can either travel along this gigaparsec without being affected by any interaction, or, and that's the main process that we're going to discuss today, it can travel and interact with one of these orange photons from the extragalactic background light. Why is that? If you are a 1 TeV gamma ray, and if you see a 1 electron volt photon, then in the center of mass there is 1 MeV squared, so that's twice the mass of the electron, so you can produce an electron and a positron. So this results in a net absorption of some of these TeV gamma rays on photons that are at around 1 micrometer in terms of wavelengths, and the production of electrons and positrons that have typically half the energy of these gamma rays. And these electrons that have so half the TeV energy, that's a Lorentz factor of about 10 to the 6, they can upscatter photons from the CMB, that is at about 1 milli-electron volts, by a factor of 10 to the 6 to the power 2, so 10 to the 12, and you end up with GeV gamma rays that you could also see possibly as secondary emission. So these are the two main processes that we're going to discuss today, and we're going to see what kind of constraints have been obtained by the community. But you can see that there are other items that are mentioned in this diagram on which I won't spend too much time. The first one up there is LIV for Lorentz invariance violation. So here the idea is that if Lorentz invariance is violated at the highest energies, close to the Planck scale, for example, for linear modification, for a first order modification, then the dispersion relation of gamma rays and electrons should be affected by a tiny effect, by a tiny amount, which could be visible at the highest energies, typically above 20 tera-electron volts in the spectra of blazes. So this is one process that we can probe. The other process that we can probe is the coupling to ALPs, which stands for axion-like particles, which are light particles with properties similar to those of axions that were postulated to solve the strong city problem. And so gamma rays can couple two axions or convert into axions within magnetic fields. Here we take the example of the magnetic field of the galaxy cluster hosting the AGN, but it could be also that of the host galaxy or that of the jet itself. And then such an axion-like particle would travel unimpeded by interactions with the EBL and could possibly convert back in the magnetic field of the Milky Way, resulting there in gamma rays that we would not expect to see. These two processes, that are beyond the standard model of particle physics, are things that we can probe, but obviously they are on the exotic physics side. Just to give you an idea of what we can probe with such gamma ray propagation, here we illustrate the energy mass scale that is under scrutiny. The low energy range, well, let me start with the center maybe. Usually when we talk about exotic physics with TV observatories, we talk about WIMPs and how we can probe them either in the galactic center or as signal from dwarf spheroidal galaxies where we don't expect astrophysical gamma ray emission. But actually we can also probe the very low mass range, typically below a few tens of electron volts down to 10 to the minus 12 or so electron volts. I'll come back to one process in the electron volt regime later on. And as far as Lorentz invariance violation is concerned, there we probe typically the Planck scale that is here. And for second order modification, we can also probe lower energies. So these are high risk, high gain scenes that are of interest to a vast community. And one thing that I should highlight here is that the studies of the classical processes that we are going to discuss in the next slides are essential to people who want to dig into this physics. And so our gamma rays, they come from the population of extragalactic sources that we have detected so far at TV energies, but also at GV energies with satellites such as Fermilat. And what is represented here is the number of identified extragalactic gamma ray sources as a function of time. So when I say identified, it means that it has a known multi-wavelength counterpart. So the story began in 1978 with the detection by COSV of 3C273, typically at above 100 MeV, so let's say at GV energies. And then a real kick arrived with the launch of EGRET. So we then reached, or the community reached 100 sources. I was far from being a researcher back then. And in 2008, a new kick was made possible with the launch of Fermilat. And you can see that now there are about 4,000 known extragalactic gamma ray sources that are mostly blue in there, meaning active galactic nuclei, but also a few orange ones, meaning GRBs and mostly long GRBs. Nowadays, Fermilat sees such extragalactic objects out to redshift of 4, which is beyond the cosmic noon, so beyond the peak of the history of star formation in the universe.
Jonathan, if I could just interrupt just for a second, your sound is coming a little muffled. I don't know if other people are hearing the same thing.
Is it your microphone down or
no, actually I'm not using that one because the sound is terrible, but I suspect that Zoom is making my computer, Zoom plus the weather, which is pretty hot here, it's making my computer ventilate. Is it a bit better now? Or?
Yes.
I think so, yeah.
Okay.
Yeah.
Thank you.
Get closer and okay.
Thank you.
So I hope you can hear me. And restarting from there, if you see the black branch there, it corresponds to observations of extragalactic sources by ground-based telescopes above 100 GeV, so the TV range, let's say. And there, the story started for extragalactic sources in 1992 at the Whipple Observatory with the detection of Mark-Lane 421. And you can see that in 2005, there were about 10 known sources, mostly blazes in the extragalactic sky, but also one radio galaxy, M87, whose matter swirling around the central black hole has been imaged now by the Event Horizon Telescope. A few years after 2010, when I was starting my grad studies, we had 30 extragalactic sources, including 2 starburst galaxies, NGC 253 and M82. And nowadays, we are at about 100 extragalactic sources detected by such ground-based instruments, be they HESS, MAGIC, or VERITAS in Namibia, Canary Islands, and in Arizona. Mostly blue sources, again, so active galactic nuclei with a jet, but also a few starburst galaxies in light orange and long gamma-ray bursts in dark orange. And nowadays, these 3 communities, as you may know, HESS, MAGIC, and VERITAS, are joining forces to build CTA, which is under construction. So most of you know about the specifics of gamma astronomy, but for those who don't, I should outline the main differences, which will have an impact on the constraints that we put. So if you take a satellite-based, gamma ray observatory such as Fermi, you have some good specificities, such as you can observe the sky in 100% of the time. Your field of view is pretty large, about an eighth of the sphere. And most of the sensitivity is actually coming at low energies below 1 TeV, let's say. This is due partly to the fact that the depth of the calorimeter that stops the electromagnetic cascade that develops in such a detector is limited, but also it's due to the size of the detector, typically 1 meter square as far as the surface, the effective area is concerned. And given our steeply falling astrophysical fluxes or non-thermal fluxes, 1 meter squared becomes limiting at some point. So the other technique that is employed at higher energies is that of imaging atmospheric Cherenkov telescopes, such as HESS, MAGIC, VERITAS. There, unfortunately, you can only observe during dark night, so 10% of the time. The field of view is limited, about 5 degrees, but you can capture such gamma rays up to 100 TeV or so, which is good. In terms of energy resolution, the numbers to keep in mind is typically 10% energy resolution for those, and an angular resolution, on the order of 0.1 degree in the 100 GeV to 1 TeV range, be it for Fermi-LAT or MAGIC and VERITAS. And just the same for HESS. I mentioned earlier CTA, and you could tell me, well, okay, the angular resolution here expected for CTA is not that much better with respect to MAGIC and VERITAS, even though there is an improvement. And there is indeed an improvement in terms of energy resolution, but where most of the improvement is coming from is the number of telescopes that will be employed, and so the effective area covered by the northern and southern arrays. So here what you see is the flux sensitivity as a function of energy, red for CTA South, gray for CTA North, compared to MAGIC, HESS, and VERITAS in orange, blue, and dark green. and compared also to a Fermi-Lat exposure of 10 years. So we will gain a lot there, and I will try to illustrate how it can help us constrain the content of voids. And let's start with magnetic fields that were constrained as early as 2010, so only 2 years after the launch of Fermi. And this was allowed by the first discoveries earlier of extreme TV blazes in 2006 by imaging atmospheric Cherenkov telescopes, in particular Hess in this case. These blazes, they have a pretty hard TV spectrum. So it's illustrated here in this plot by this dashed line. So that's flux as a function of energy. Here we are at 1 TeV. And their intrinsic emission, meaning emission after having corrected for the absorption along the line of sight, is expected to be pretty faint in the Fermi-Lat band. Now, as mentioned earlier, the gamma rays that we lose between this dashed line and the dotted line, that is the observation by Hess, their energy ends up being reprocessed at lower energies, at GeV energies. Typically, this is 1 GeV, this is 10 GeV, due to this upscattering of CMB photons. Except that when Fermi started to observe, and this is the sensitivity of Fermi here, nobody could see 1e(SO229) at GeV energies. So from this lack of observation, Neronov and Vovk in 2010 concluded that one way out of the problem consisted in deflecting the electrons and positrons that would then upscatter the CMB photons, deflecting them away so that you would dilute the secondary signal beyond the PSF of Fermi, and so you wouldn't see it. Nowadays, we actually do see an object such as 1e(SO229) in the GeV band. These are the red points here. The spectrum is indeed pretty hard, as expected from the earlier modeling of the TV emission. And even the fact that we do see such a hard spectrum allows us to constrain the maximum amplitude of the minimum amplitude of the magnetic field. The latest constraints that have been obtained in that matter have been obtained thanks to the combination of the TV spectra with the GeV spectra observed by Fermi-Lat and the morphology of Fermi-Lat. I showed you earlier that the PSF, the point spread function of Fermi-Lat, is about as good as that of Veritas, Hess, and Magic in the 100 GeV range. And so that's here the idea. We exploited a catalog of extended sources at high galactic latitudes, where we couldn't see any extended emission in TV blazes, to jointly fit morphology, spectra, and constrained magnetic fields in voids with this technique. What you see here are the constraints obtained from mostly extreme TV blazes. 5 of them are extreme TV blazes. So that's the magnetic field on the y-axis and the current length on the x-axis. The one that is in yellow is 1e(SO229). It's one of the most constraining one. But actually, if you take another extreme blazer like 1e(SO347), it's almost as constraining as 1e(SO229). And when you combine these limits, you end up with the constraints that are shown on the right-hand side. And such constraints depend a lot on the assumption that you make for the activity timescale of the source. So typically, if you assume that it's been active only for the past 10 years, you will end up with a limit that is at the level of a few times 10⁻⁻16 Gauss for these combined constraints. While if you are more optimistic about the activity, you can end up to very strong constraints. In practice, the constraint that we quote is this blue dashed line here that corresponds to the simulation setup, the limits of the simulation setup used to process or to generate libraries of the GeV morphology. Now there is an alternative cooling method for such gamma rays. I should go a bit faster, which are plasma instabilities. So I mentioned the Compton scattering, but an alternative way, for this focused and not dense at all beam of electrons and photons propagating in the intergalactic medium to lose energy is through plasma instabilities that would develop on the edges of this beam. And what is shown here on the left, on the bottom left side, is the energy loss rate, let's call it like that. You can see that it's in units of megaparsec -1 as a function of energy. Inverse Compton scattering on the CMB is the gray line, and the colored lines corresponds to different instabilities that have been studied in the literature, which would mean that their rates or the energy loss rate associated to these instabilities would be larger than the inverse Compton scattering, which could result then in energy loss through these plasma instabilities and then hitting of the intergalactic medium. It's been simulated actually by the colleagues who promoted such instabilities, in particular Broderick et al. In 2012. And you can see on the right-hand side what the intergalactic medium in a 100 megaparsec box could look like at redshift equal 2 without such a hitting or with such a hitting. One of the main difficulties in this alternative cooling method is that it's unclear whether it's a viable energy loss mechanism because analytics are, in a sense, not sufficient. You need the numerics that go with it, and the number of orders of magnitude that go between the typical lengths associated to these instabilities and the development, the size of development of these intergalactic cascades is huge. So that the situation, even on the theoretical side, is unclear at this stage. Note that there are some discussions about a possible observation of such a eating through the Lyman alpha forest. I think that if we have such an observation, that would likely be the smoking gun for such a process to occur. Still, the mainstream constraints keep on assuming that the energy losses are due to Compton scattering, and so that they can help us constrain the intergalactic magnetic fields. You can see actually here on the left-hand side, two slices of the same simulation that I showed in the first slide, where different assumptions are made. So in color code, what you see here is the strength of the magnetic field. This is log 10 of microgauss, so 10 to the -3 is in green here, and so that would be about 10 to the -12, sorry, on the Gauss on the right-hand side plot. So here, the colleagues assume a primordial origin of the magnetic field that's before recombination. And in the second case, sorry, an astrophysical origin, meaning pollution from galactic winds or from the jets of AGNs. And you can see that the magnetic fields involved would be completely different. With CTA, likely we can constrain actually these astrophysical origin scenarios that correspond actually also to the green box that is here. So let's see what we can do when CTA is launched or when CTA gets started. To also discuss this in the multi-messenger and multi-wavelength context, sorry, I illustrate here on the left-hand side. So again, we have magnetic field strength as a function of current strength. The 5 sigma rich that we can get with CTA observation of a single source, 1ESO229 in 50 hours, compared to the constraints that have been obtained from the observation, sorry, of an ultra-energy cosmic ray dipole or dipolar signal above 8 eV, now detected with about 6 sigma significance. And this dipole is not too far from the dipole expected from the distribution of galaxies, of infrared galaxies within 200 to 300 megaparsecs. This rather good alignment can be used to then try to constrain the intergalactic magnetic field, and this is the limit that they placed. There are also other competitive limits, obviously, from CMB anisotropies, but that's for a specific scenario, a primordial origin in this case. bottom line here, the take-home message is the phase space is shrinking, which is good. Maybe we'll get a chance to detect such a signal or to exclude a good fraction of the parameter space and then help our colleagues working on theory to understand the origin of cosmic magnetism. On the right-hand side, you can see another illustration of a multi-messenger constraint. I won't dive too much into it if I want to discuss the EPL. Let me say just in a nutshell that some colleagues working on theory try to relate the signal that has been observed with nanographs. So we are talking about pulsar timing arrays there. It's not clear at all at this stage if it's a primordial signal or not, but there is an excess of signal. And so they try to interpret it in a scenario where a primordial magnetic field would have a role or would play a role and would generate then the magnetic field that we observe today. This is something that CTA could probe as well. And that brings me to the quantity that we can measure, actually, which is the content, the light content of void. So how much light is there in these big regions? And to illustrate that, I start with the night sky brightness, or to be more specific, the specific intensity of the sky, of the extragalactic sky, as a function of wavelengths. And you can see that we have in this spectrum of the universe two bumps here called the cosmic optical background and the cosmic infrared background, whose integral, whose energy density represents about 6% the energy density in the CMB. These two bumps constitute the extragalactic background light. That's the second most intense cosmic background after the CMB, and the most intense one of astrophysical origin. So the cosmic optical background itself is coming from direct starlight escaping from its environment, from the host galaxy, and then being redshifted from UV or blue wavelengths up to the near infrared, around 10 micrometer at max. And part of it also comes from active galactic nuclei, although it's likely a small fraction, typically less than 10%. The second bump is due to the UV blue light that could not escape from the environment of the star or the AGN that ended up hitting dust around it. And this dust re-radiates then in the far infrared with a peak typically at 100 micrometer. We have constraints on this amount of light that fills the voids in the universe. First, from direct measurements. So the idea there is that you look at a dark patch of the sky and you try to see how dark it is. If you are doing that from Earth, air glow will be a problem. But even if you do that from space, the first foreground that you will face is zodiacal light, ZL here. You can see that it's typically 500 nanowatts per meter square per steradian at around 1 micrometer. When what we are looking for at 1 micrometer for DBL is typically 10 nanowatts per meter square per steradian. So a factor of 50 there. Means that when you want to subtract this background, or this foreground, sorry, the zodiacal light, that comes from dust within our solar system, and that has a geometry that is a priori known, so along the plane of the ecliptic. If you make a 2% mistake, then you will make a 100% mistake on the residuals that are the level of 10 nanowatt per meter square per steradian. So a very good precision is needed there. Even when you've managed to subtract such zodiacal light, you have to pay attention to stars that you should mask or remove, and to diffuse galactic light. So typically cirrus clouds that will radiate also in your wavelength of interest. So this is a difficult technique, and that's why you can see that actually these lower pointing triangles, great iron triangles, they end up unsurprisingly overestimating the amount of CDL. I will come back to this point later on because it remains a very interesting point as of today. The second technique, which is probably the most robust, but which slightly underestimates the amount of EBL, comes from galaxy count. So there the idea is that you look at all the galaxies that you can in a given field or in multiple fields to minimize cosmic variance as a function of their brightness. So magnitude is shown here. And you reconstruct the luminosity function of these objects. You hope that you observe down to or up to a magnitude that is sufficiently high, down to a flux that is sufficiently low, so that you catch most of the light. And this is what is illustrated down there. You can see the cumulative amount of light as a function of magnitude. So larger means fainter flux. And with the latest constraints obtained by the Gamma team, this is the state of the art. We do see nicely this convergence, and they are able actually now to reconstruct the amount of EBL from known galaxies at the level of 5%, if not better, around 1 micrometer, which is pretty impressive. And the last technique is the gamma ray technique. So there we have to rely on what we know from particle physics. So that's the pair creation cross-section that is there. We have to rely on what we know from cosmology. That's the distance element dl over dz that is here, which includes in particular the Hubble constant, or omega matter and omega lambda. And also, we hope to constrain these optical depths here so as to infer the amount of EBL of astrophysical origin or else that is encoded in this dn over dE here. What can be shown actually is that in the local universe out to redshift, out for sources out to redshift of 0.6, 0.7, you can simplify a lot this formula, and you can express the optical depths as a convolution product between the spectrum of the EBL that is here and the integral of the cross section over the line of sight. And that's the EBL kernel that is shown here. Net result, if you look, for example, at a source that is at a redshift of 0.003, which is taken as the redshift of 0.421, the closest blazar that we have, you will see absorption mostly coming from interaction with photons of the cosmic infrared background. On the contrary, if you take a source that is far away at a redshift of 0.6, which up to 5 years ago or so was the most distant TV blazar that we had, they will interact mostly with the cosmic optical background. And in between, sources will interact with both kind of photons, and the inflection point that you see here in the absorption feature is actually related to the dip between the COB and the CIB. So by reconstructing this spectral feature as a function of energy and redshift, you can hope to reconstruct the amount of EBL that is out there. I illustrate that here with some models that were up to date in 2012. I'll show you afterwards what happens with the latest models. Again, to come back to what I was saying earlier, 20 TV photons from a nearby source will interact mostly with photons from the cosmic infrared background, while if you look at a source at a redshift of 1, with photons at 100 GeV, they will mostly interact here with the cosmic optical background. You can see that here we can tell by eye differences between the models, and these differences actually you can try to trace them back to the plot that is on the left. It's an exercise to be done. The 3 types of models that are here are completely different in terms of the way they were built, so that the rather good agreement that they bring on the cosmic optical background can be comforting and can tell us that on the modeling side, we have a good handle on what happens there. This is what happens with the latest models as of today. And you can see that, again, the curves are pretty much similar. Actually, the 3 models are pretty similar here because they all try to reproduce galaxy counts. So it's not surprising that they end up with similar intensities. What changes, though, between the models, and this is what you see on the right-hand side, it's the evolution of the EBL itself that differs from one model to the other because you base this evolution either on the global cosmic star formation history, for example, or on empirical local data. And these are the constraints that this is a summary of the constraints that we obtain with TV astronomy as of today. So what we do, the simplest approach that we have, consists in saying that the flux that you observe at an energy E from a source at redshift Z is an intrinsic flux that depends on some intrinsic parameters times the absorption term, and your free parameter is a scaling factor alpha with respect to a given EBR model. You try to find the best alpha for a set of free or fixed parameters, depend on the S's, and you reconstruct then the normalization of this optical depth that is shown here on the y-axis. It's shown as a function of the source of the redshift of the gamma ray sources that are used by the S's. And you can see the first constraint that were obtained, for example, by Hess in 2013 in dark blue here. It was a 9 sigma signal, or by Fermi in 3 redshift bins, and it was a 6 sigma signal. Now, such measurements have been confirmed by current generation IACTs, and here you can see a compilation of analysis, either of reanalysis of GV data in pink, of a collection of TV spectra in light blue, or the magic results in darker blue. Note that so far, the summary results that are indicated here only use about a third or half of the data that have been collected by current generation TV instruments. So I'll come back to that later on. One thing that I should highlight as well here is that what is crucial, obviously, in this game is how you model the intrinsic emission. If you put too many free parameters in the intrinsic spectrum, then you will end up overestimating the uncertainty in the EBR normalization, possibly without bias. If you put too few parameters, if you assume, for example, that you can know your spectrum from synchrotron self-counting models, then maybe you will constrain too much the intrinsic spectrum, and this will bias the estimate of the amount of absorption. So what's critical there is to perform the analysis in such a way that the results are statistically sound when you study a sample of TV spectra. And here is an illustration of what CTA can do. So these are the orange points that illustrate the statistical uncertainty on the normalization of the EBR that can be obtained with CTA, down typically to 5% in the redshift range where we are most sensitive with ground-based instruments, so typically between 0.1 and 0.3. And the light blue regions show here the systematic uncertainties that could be reduced also by a factor of about 2 with respect to current generation instruments. One thing that should be noted also, or as well, sorry, is that we could go with CTA up to redshift of 2 for the detectable sources when we go only to redshift of 1 with current generation instruments. Okay, so in the 10 minutes or so that are left, I will try to discuss not the EBR model dependent approaches. So what was shown here is what is the scaling factor with respect to a known model or to a model that you assume to be known. Now, what can we tell about EBR model independent constraints? Such constraints are illustrated here on the right-hand side with a few sets of analysis. So that's still the night sky brightness as a function of wavelengths. In red, EBR model independent constraints on the intensity from Hess, and from in green from a study that we made with, at SKIP in 2015. In yellow, you can see the constraints obtained with Fermi-lat. Actually, a note is in order here. They don't aim in this work at reconstructing the EBR spectral energy distribution per se, but rather the cosmic emissivity. That is the amount of light that is emitted in each shell, onion shell of the universe. So that such a band cannot really be qualified, in my opinion, as an EBL wavelength-resolved measurement. So we are able, with only TV instruments, to constrain, you can see in 4 bands, the EBL. It's not far from galaxy counts. Actually, there are systematics that are not highlighted in this plot by Gosai et al. 2019, but the points are consistent within statistical and systematic uncertainties. The only thing that we can say as far as the low wavelength regime is concerned is that the intensity of the EBL is typically below 15 to 25 nanowatt per meter square per steradian, and the results from the 3 major collaborations agree rather well on this. Now, if you look at galaxy counts that are estimated now with unprecedented precision, it's typically 8 nanowatts per meter square per steradian. And there was a recent direct measurement published in 2020 by Lower et al., by Todd Lower and Mark Postman, that was made beyond the orbit of Pluto with the New Horizon probe and the LoRa instrument on board of it. What's good is that beyond the Pluto's orbit, you would expect the amount of zodiacal lights to be pretty faint. But when this result was published in 2020, my first reaction was, okay, it's 16 plus or minus 4. So indeed, it's a factor of 2 above galaxy count, but the uncertainty is pretty large, so it's just a 2 sigma effect. It could be a fluke. Now, actually, this year, very recently, they've published a new observation or reanalysis of the LoRa data. They had analyzed 7 fields in their first paper, and they found an 8th field where the constraints can be obtained with much better precision. And in this darkest reliable field obtained with New Horizons, they now claim an uncertainty of about 10% at 0.6 micrometers. So that you can see now we are at 16 plus or minus 1.5 with respect to 8 nanowatt per meter square per steradian expected from galaxy counts. That would imply in practice that we've resolved only half of the EBL. This is something that I illustrate also in this right-hand side plot. So you can see in green the constraint from galaxy counts. The star here is the constraint from New Horizon beyond Pluto's orbit. And in blue, the gamma ray constraints. What is there remains a mystery as of today, but I'll try to highlight briefly the hypotheses that have been brought forth. The first one is exotic physics. So I mentioned earlier the coupling of axions with gamma rays in magnetic field. Actually, this allows us to probe the very low mass regime, where you can see the symbols Hess, Mach N41, Fermi here. What we are interested in this case is not this very low mass regime, but rather the 10 electron volt regime in which axion-like particles could decay in 2 photons that end up about at the right wavelengths to result in an excess of light at 0.6 micrometer. Note that if that were the case, if one tries to explain, the excess, the twice larger night sky brightness from these axion-like particles, one has a hard time explaining it by assuming that axion-like particles are standard cold dark matter. This is outside of the range of interest. And a recent paper also studied that recently, and they indicated that if indeed the New Horizon signal was explained by axion-like particle, and if axion-like particle were all of dark matter with these properties, with a few eV mass, then we would expect to see fluctuations in the field of the Hubble Space Telescope below the arcmagnetic scale that are not seen, so that it does not seem to be a viable explanation. Another possible explanation that has been discussed also for a long time lies in the faint galaxies. So galaxy counts, ultimately what they do is that they reconstruct luminosity function. Here it's the stellar mass distribution or function, and they extrapolate it down to low masses or low luminosities to determine how much light is missed. We can do that either in deep fields or for sky. The stellar mass functions that are reconstructed are pretty consistent across these ranges. But one could say that, for example, there is a population of low surface brightness galaxies that we have missed. Or one could say that light in the outskirts of galaxies, in their wings, in their halos, has been missed. All of this has been estimated, and it's estimated to less than 20% of the total amount of EDL. But still, it needs to be checked and studied in detail. And the recent launch of the JWST will certainly be helpful for that matter at higher redshifts, but also at lower redshifts. And the final explanation that will end our trip before the concluding slides will bring us back to our very vicinity. So we started in voids gigaparsecs away from us. Let's come back to the solar system. What you see on the left-hand side here is the brightness of the sky again as a function of wavelengths, and the zodiacal light spectrum is shown here in green. There are two measurements that have been made recently, or one estimate and one measurement. One with Hubble Space Telescope data, the SkySurf program led by Roger Windhorst and Timothy Carlton, where they aim basically at realizing all 250,000 exposures of Hubble and to model all the foregrounds and sources in there, so as to extract the best direct measurement possible of the EBL. They only analyzed a fraction of it as of now, and they do see a small excess. This excess is very much in line with an excess that has been also observed with a rocket, Cyber, that was launched in the past years, and that is equipped with a spectrometer, and that could observe in particular the carbon-2 triplet lines, which is a good tracer of zodiacal light. What they inferred from their observations is that when you take the best geometric model or the best physical model that we have of the zodiacal light, which comes from Kielsaur 1998, they do see an excess in terms of amount of light that is about an offset that is about 15 nanowatt per meter square per steradian. That looks pretty much isotropic, and adding this access to their data fits very well their measurement in CA2. The competing model from right, it's less constrained by geometry. Let's say that it takes into account this possible isotropic component at the expense, though, of fitting the data much worse. So they conclude from this study that there might be an isotropic component in the zodiacal light around us. And if such a zodiacal light came from beyond Pluto's orbit, that would also explain the signal that has been seen by Lower et al. With New Horizons. So I think that there will be a lot of excitement on this topic over the coming months and years. At least this is exciting to me. And so to summarize and try to conclude on this, I was a bit long, I'm sorry about that. As far as gamma ray propagation is concerned, we are moving towards measurement with typical uncertainties of 20% down to measurements with uncertainties of 5 to 10% with CTA, and that's very good because we'll become competitive with galaxy counts, so that we can have either a good probe of the EBL if this is what is of interest to you, or very good probes of exotic physics if this is your cup of tea. One thing that we are studying in my group as we speak is particularly the impact of the intrinsic emission model. And so we are developing a fully Bayesian approach to tackle this open question of the number of intrinsic parameters, and also to account fully for the instrument-induced uncertainties. With CTA, we'll be able to probe DBL not only up to redshift of 1, but up to redshift of 2, which corresponds to the peak of the star formation, the cosmic star formation history. The question is, can we constrain this cosmic star formation history better than Fermi-Lat or not with CTA, or with the combination of both? And what kind of accuracy can we get on the Hubble constants? Because such gamma absorption measurements have also been used to constrain it. And we still search for the secondary gamma rays. So I've tried to illustrate how this absence of secondaries can be exploited to constrain magnetic fields in voids. But we should keep in mind that this is under the hypothesis that this is the main energy loss process, meaning Compton scattering, and plasma instabilities are still discussed. I suspect that there the main progress will come in the coming years from simulations and theory, also possibly from Lyman alpha observations. If we want to address the optical controversy before CTA comes up, I think that the best would be certainly to put together Hess, Magic, and Veritas data in the CTA format and analyze them together. I understand, though, that this may be politically difficult. So what we are trying to do as of now, through a collaboration between my institute, SKIP, and colleagues from Spain, is to gather all archival data from TV instruments and to analyze together these archival data. This is a work particularly led by Luca Greo, my grad student, and we are getting very exciting results. One thing that I want to propose here today, and that I've started discussing with colleagues, is given the developments in terms of measurements of galaxy counts, this new 4 sigma evidence with New Horizons, and the latest updates from TV observatories, putting the 3 communities around the table to make a status on DBL may be interesting. So I've started gathering opinion about a 3 to 5 day workshop in the Paris area in late 2023 or beginning of 2024. And that brings me to my very last slide. I've talked a lot about CTA, but actually the observations that will start in the coming couple of years with CTA will be nicely complemented with the constraints that we can obtain on the low end of the galaxy luminosity function, for example, with JWST. Also, redshift surveys and spectroscopic surveys with such satellites. One satellite that I would like to highlight here is the Messier satellite that will observe the full sky if selected by ESA in the low surface brightness regime. That would be pretty helpful to understand better zodiacal light, the amount of interstellar light as well, and to probe DBL through a new technique that is developed and that was successful with Galax, which is broadband intensity mapping. And so all of this will help us understand the light in voids and how much faint galaxies we may be missing. As far as cosmic magnetism is concerned, I should highlight SKA here, probably mostly for clusters and filaments, but that will help constrain model, I suspect. And Auger still, the Pierre Auger collaboration still has a word to say on this. That's assuming that we have a better understanding of the sources over the coming years, but there is some hope for this. And I will stop here. Thank you very much.
Thank you. Thank you very much, Jonathan. That was great. Paulo, are you?
Okay, sure. So I guess there was lots of things in here, different things. So we could open up to questions now about specifics in the talk, or in general, if it's an open discussion now about what we can learn about the universe using extragalactic probes, I guess, is the more general topic. So does anybody have questions? And I see John Mitchell raised first. So go ahead, John, ask your question.
Yes, I do. Okay, thank you. I'll lower my hand just so it doesn't linger there. All right, so Jonathan, thank you very much. That was a great talk. and I think I largely understood it, but not perhaps all. So I'm left with a couple of questions. The one specific one, I understand I believe the absorption by the optical light by Compton upscattering, well, optical and CMB. What I didn't quite get was how, if at all, one could untangle axion-like particle reprocessing by the combination of producing them in the source region and then reprocess. Yeah, this plot, you've got a couple of uncertainties in there. The two magnetic field regions seems to me to make life difficult, and of course, that's going to also give you a signal that must, in some ways, compete with the upscattering signal. How do you possibly untangle all that?
So I'm not the world specialist on this, the world expert, but I know a bit about this. So let me go through it. So you're completely right. There are uncertainties in such approaches, and one of the strong one is related to the magnetic field. If you take the magnetic field in a cluster, we know it's about 12 for the coma cluster, and that's about it. And then in the host galaxies, it's pretty hard also to probe. In the jet, it's highly debated in the community, and it depends also a lot. It depends a lot on where we suppose the gamma rays are emitted. But now, maybe the question I can try to answer is, what are the signatures that are specific to such a process? So I will go to my backup slides, and I will try to show that. I hope I have it. Do I have the CTA constraints? Yes, okay. Okay, let me start with this one. There are actually two signatures that are looked for, and the easiest one to constrain are these fluctuations here. In this plot, what is shown is the simulation of a flare from a nearby radio galaxy, rather nearby, with classical absorption in dashed. The blue points correspond also to the simulation of CTA points for this classical process. And what would happen for a specific realization of the turbulent magnetic field in the cluster, in the Paris-Sud cluster that hosts NGC 1275. And the fluctuations that we see there are directly linked to the fluctuations that are in the magnetic field. So if you don't see such fluctuations, then you can exclude part of the parameter space. And this is what is done on the right-hand side. And then there is another way to probe such axion-like particles. And I have to go to another slide to illustrate this. Hope my reply is not too long. The other way is illustrated on this bottom right plot. So you can see in this purple curve here, some fluctuations that have actually been smoothed at the resolution scale. But there is also an excess of expected number of gamma rays at the highest energies, which is related precisely to these gamma rays converting into axions in the vicinity of the source, either jet environment, galaxy environment, cluster environment, and then converting back in the magnetic field of the Milky Way. So they are unimpeded by absorption, and that's why we could see them. So these two things are what people use to probe axion-like particles. But
right. Okay.
But still, magnetic fields do play a role. And for example, in the CTA constraint that I illustrated, this is something that we discussed. This is the main source of uncertainty.
Very good. Now, my second question, which is sort of answered, I think, by this slide, is the value, if at all, of going to MEV energies.
Of going to MEV energy?
Oh, the gamma ray sectors. Yeah, well, for anything.
So for axion light, so the question is about axion light particles or LIV or both?
Both.
That's a tough question.
Well,
I told Rashmi that I wouldn't talk about exotic physics, but I'll do my best, and I hope I won't say.
Well, you can make it short. It was just as a person involved with MEV detectors, there's always a search for science cases.
Yeah. So axion light particles, MEV images, I must say that I don't know, because otherwise I'm not convinced about what I would say. I suspect that you would probe a different region of the parameter space, but I'm not expert enough to make a strong claim here. So I will, sorry, I won't answer.
Okay.
LIV from memory, polarimetry at MEV images is pretty competitive with other constraints. So there is a strong science case, and it's been discussed for Amigo and for EF program. So there is a vast literature on this.
Yeah. Yep.
And sorry, and just then a comment, which is just a comment. I believe what you've shown basically is that continuum sensitivity is the important thing in a direct gamma ray detector. But I'll mention just as a point that in your space-based measurements, you might include CALET, which has a 30 radiation length deep calorimeter, and at the higher energies, 1% energy resolution. Now it's relatively small and it can't be pointed at a source because it's attached to the space station with no scanning, but nevertheless, it's a player in that that region with excellent energy resolution.
Okay. So I must admit, and I'm sorry about that, that I'm not that familiar with CALET. Has it been running for a long time? And
it's been running since 16, or is it 15? 2015.
Okay, I should look closer at it and just to see the sources that have been detected so
and
far.
If you find that you're interested in it, I'd be happy to. Rashmi would know how to get in touch with me. I'd be happy to get information on it. I've been involved with it since its inception, so it and I are old friends. All right, well, thank you very much. It was an excellent talk.
Thank you.
John, could I ask you one other question? Is AMS any good for this, for the similar reasons as CALET? Or
wouldn't think so. It doesn't do gamma rays really at all.
Because I've seen plots of like gamma ray sensitivity, which is actually close to Fermi in the very old days, but I never heard anything since then. So,
well, yeah, I'd have to think about it. I mean, CALET is by definition a gamma ray detector because it's a high energy electron instrument.
Yep.
And so, but it does it by calorimetry, where most of AMS's performance is magnetic spectroscopy. Now, it does have a smaller calorimeter, but it's both small and thin. So I doubt it plays much. I mean, it has some sensitivity, but probably very little in this context.
Okay, thanks.
Thank you.
Okay, if nobody else, then we should go to Evgeny. Second hand up. So, are you still there, Evgeny?
Yeah. Thank you for this enlightening talk. And I agree that new physics is always exciting, but my questions are about the ordinary physics. First one is concerning the duty cycle of blazars, possible duty cycle. If we are talking about the processed radiation from TeV to GeV in voids, then it can be smeared in time over a million of years. So then we see some kind of average over a million of years. And it's easy to imagine that nowadays blazars, which we see now, they are more or less in active state and say few times brighter than on average. If, for example, you just divide by this few times the expected secondary signal, would it constrain anything?
So your question, if I understand it well, I'm trying to go to full screen, I'm sorry about that. Your question, if I understand it well, is what is the impact of the duty cycle, the constraints that we set on the intergalactic magnetic field, and what range of duty cycle is reasonable? Do we understand the question correctly?
Yeah, yes.
Okay.
You can reformulate it like this, yes.
Yeah. Okay. So I can tell you what the Fermilab collaboration did for this paper, because this is the part that I contributed to in this paper. There is the pessimistic assumption, often cases, which consists in saying the blazars that we observe have only been active for 10 years. And this is completely pessimistic because we assume that only during the time when we observe them, these sources were on. So it's purely driven by observation, not at all by the physics of the source itself. Then there is the typical activity timescales of such objects that are inferred from either population or from physical arguments, time growth of black holes. And there you end up with 10 to the 7 to 10 to the 8 years. And that's the constraint that is shown in orange here. And we said, okay, we're going to take a third case, which is in between 10 to the 1 and 10 to the 7. That's 10 to the 4 years, 10,000 years. And you end up with the purple area. So what is the impact of these different assumptions? If you change by 3 orders of magnitude the activity timescale, you get a constraint, sorry, that is 1 order of magnitude better on the magnetic field. This is what we see here. So it has a strong impact. Noting, though, that here in this publication, we said we limit ourselves to 10 to the minus 15 in this case, goes, which is the breaking assumption for this CR-propa simulation that we did. So is this a satisfying answer? Again, the range of activity timescales that are considered are either, in my opinion, too pessimistic. We use 10 years based on observations, but we know that blazars have been active for more than this. And sure, they can be flaring at the time that you see them, but actually when you look at extreme TV blazars, and I suspect that Luigi discussed that in a previous seminar, they are not that variable. They are rather steady, at least in the TV range. So it could be that they are a factor of 2 brighter now than they were 20 years ago, but it won't change much the constraints that you put on the IGMF.
No, not sure that I got it completely. The strength of the reprocessed signal is proportional to the strength of the TV peak, more or less. If you say, yeah. Yes, so integrated over, say, million of years. Now, if you say that during this million of years, the TV peak was on average, say, 10 times less bright than now, then I don't think that it will be above the error bars, the expected secondary signal. I don't understand how you can get any constraint.
So you can, I see your point. That's a question I suspect that was also raised in the literature on this specific study. One thing I think that this study brought is the fit of the GV morphology. So you don't fit only a spectrum. So it's not only a matter of do you fall below the GV spectral points, it's also a matter of is there any extended signal? And in the rather strong magnetic field regime, this extended signal or the lack of extended signal is a good way to put strong constraints on the IGMF. Does that help?
I see your point. Not sure that I agree with 100% agree, but yes, I see your point. Thank you. And second question is different. When you showed a slide about possible influence of plasma instabilities, then if by any chance you can say what exactly was the plasma instability that is supposed to drain particles' energy? Because usually they act completely differently. They isotropize particles, but they don't drain the energy. And if you don't drain the energy, it's nothing.
So by memory, well, okay, we can. I can answer your question. I suspect without answering it completely. You can see that the energy dependence of each of these rates is different. So actually, these answers consider different plasma instabilities. So my answer is no. I can't tell you which one. We have to go and check in the literature. One thing that I would recommend, if interested, is to go and look at this review by Rafael Alves Batista, where he provides all the reference and he gives an overview. But then this is admittedly a topic that is beyond my skills. I can try to understand what they say in the paper, but I'm not a theoretical physicist working on plasma physics, unfortunately.
Okay, thanks anyway. Thank you.
And I'm not diminishing the importance of plasma physics. And by the way, this is a super important field for what we do.
Okay, good.
Yeah. Okay, we could go on about plasma physics, but we're not going to finish that today. So maybe Manel, what's your question? Let's see.
Hi, Jonathan. Yeah, thanks for the talk. It was great. Hopefully a short question. So for axion-like particles, we're always placing constraints by hoping that the photon converts into an axion-like particle and then converts back into a photon, and we see gamma rays that we wouldn't expect to see. Is there any room to make constraints just using the fact that some gammas would disappear into ALPs and we would never see them again? Is there any spectral feature that we could try to look in that channel?
So the answer is yes. Let me try to show this plot again that was obtained for NGC 1275 and with the simulation. It's less clear here. Where are you? Up. So you see the orange line in this left-hand side plot. This is precisely what you are looking for. This is the signature that is used to say, look, part of the gamma rays disappear because of their coupling in the turbulent magnetic field of the cluster. And this is the signature that is used in this case, both by CTA and Fermi-Lat to put constraints on axion-like particles. The regions that you see in the back here from Hess and the region that is called TV transparency, what they looked for is the other thing that you were mentioning, meaning a signal at higher energies, or to be more accurate, a signal at high optical depths. That answers your question, Manel? Yeah,
so it's basically we don't have the energy resolution to see those narrow dips. That's why.
So you are right. If what matters then is the smoothing of this curve with the energy resolution of the instrument. The way the Fermi-Lat analysis was performed and the way the CTA simulations also were performed was by oversampling the model and taking into account the energy resolution in the oversampled spectrum. And that's how we determine that this region can be probed. That makes sense? Typically, we are displaying our sensitivity curves with 5 bins per decade, if I'm not mistaken. And here we typically oversampled by a factor of 2, 3, 4, but accounting also for the energy resolution in the analysis. So you have some sensitivity, to these features when they are strong enough, and that's why you can go down to a coupling value of the image.
Thank you.
Sure.
Okay, any more questions? If not, I can ask my own question, but let's see if anybody else has a question. Okay, so my question would be related to systematics again. So I was taught in the old days that imaging Cherenkov telescopes can't measure absolute energies to better than 15–20%. Is that true? And how does that mess up the tau? How do you guys take that into account?
That's a very good question. How can I answer it? I can answer it like that. So this 15 to 20%, it's actually probably a bit better than this. I suspect we still quote in the Hess Magic Veritas paper 15–3%. I'm not in Hess Magic Veritas anymore, but when you look at analysis or reanalysis of the Crab Nebula as observed by Hess Magic and Veritas, and as observed by Fermilat, which has a much better absolute not 0 point, but absolute energy scale, then the typical dispersion is 10%, maybe a bit better. So that's one way to comfort yourself that your energy scale from the ground is not too crazy. Then one can always argue that rescaling your flux by 10% like this can be equivalent to rescaling in flux and rescaling in energy by much more. So, okay. Now, how does it impact our analysis of the EBR? You'll see that the answer is by not much. And the typical uncertainty on the EBR normalization that I have in mind is 7 to 8%. I'm playing with memory here, so why is that? Because the absorption feature that we probe here, you see that it's on broad energy scale. It spans an order of magnitude in energy. So the question is, what will happen if you shift left or right such a kernel that will result in through the convolution with the EBR spectrum in this curve. And you can see that this 10% effect or 20% effect on the energy scale is not is pretty small with respect to the width of the kernel itself. Saying that the width of the kernel is large is another way of saying that we are looking at broad energy scale features. Still, if we want to be competitive with our colleagues measuring galaxy counts with a precision of 5 to 10%, this is an effect that we need to take into account. And so the way I want to do it, particularly right now, with this pre-analysis of archival data, but I have the same thing in mind for CT in the future, is in a fully Bayesian analysis, you account for this parameter and you marginalize over it. In a frequentist analysis, you would find the best fit energy scale somehow. And I think that we can probably gain a couple percent precision on the measurement in the end with such an approach. But it still needs to be demonstrated.
Okay, thanks. Got one more question, but any other questions from other people?
Sorry, Paolo. Hi.
Go, Luigi.
I'm Luigi. Sorry. Just a comment and a curiosity. The comment is indeed these extreme lasers and 0229 in particular are not varying much, a factor of 2 or 3 at most for what we've seen. But especially at TV energies, even if the uncertainties are a bit high, but I think both Hess and Veritas integrating over different periods and so on gets more or less the same flux within a factor of 2. And this is, in fact, has been used somewhat as a possible indication that maybe we are looking at it wrongly, in the sense that it is maybe the TV part which comes somewhat diluted in time, let's say, of a higher active phase of the source, and instead the X-rays correspond to the usual jet. But on a different argument, what about the size of the voids? I remember that some time ago they were considered about between 50 and 100 megaparsecs, the size. While now, from your slides, Jonathan, I've seen they are considered more about on the order of 10, 20, 30. Did I get it wrong, or?
No, you get it right, and in a sense, you are both right and wrong, or I am both right and wrong. Let's put it that way. If you consider how will I like this up, tack, maybe this one. Forget about what is down there. We don't care about it for discussion. What you see here is the amount of light expected from star-forming galaxies or from stellar mass. It would be the same argument. And you can see that, and so in three different onion layers. First layer from 0.01 to 1 megaparsec, mostly the LMC is shining, then 1 to 10 megaparsecs. Actually, here we see the supergalactic plane, and this is the local sheet. One of the structures that I was mentioning earlier, in between filaments, typically 6 megaparsec radius. And you can see what is highlighted here as the local void, that is also called Tully's void, which is a void above, in the right coordinate system, the local sheet. You can see that it extends up to almost 300 megaparsecs. So this is indeed a big region, a pretty deep region. Now, the scales that I gave in my, so you are right, there are huge voids that are inferred to have sizes or lengths on the order of a few hundreds, a couple hundreds megaparsec. What is highlighted here is a simple model developed in this paper where they want to recompute the volume filling fraction of clusters, filaments, sheets, and voids, and to reproduce the volume filling fractions that are inferred from simulations such as this one. This is actually not the simulation that they quote. This is the simulation from Forero and Romero. They need filament width divided by unit cell length of a tenth. So basically, if you try to take your filamentary universe and put it in a crystallographic model, then you would have a factor of 10 between this 1 megaparsec and this 10 megaparsec. Now, we know that the universe is not a crystal like this. And so there are some voids that are much smaller than 10 megaparsecs and voids that are much larger than this. Here is just an illustration to give the typical sizes that should be considered within a simplistic model.
Okay, and, but the observations, somewhat what they say about, let's say, the few voids that are around our local cluster.
So
if
this tough game. I suspect I would need some Lyman alpha experts in the room. I'm not one. What I can say, based on the literature I've read on this topic, is that volume filling fractions are often inferred from simulations. Because this is the easiest way to do it. And then these simulations can be constrained so that they reproduce the spatial distribution or the velocity distribution of nearby galaxies. This is what is done here in this case. And to be even more convincing, you can see that in this case, we have a box of size 200 megaparsecs, so that indeed 10 megaparsec does not seem crazy. That does not mean that there aren't deep, big voids. It's just mean that it's a typical size, assuming a very simplistic model. That still gives one, I suspect, the scales in mind. And it works pretty well, actually. The local sheets in which we live, for which we have a very good mapping, because we can map the galaxies around us. It has a radius of typically 6 megaparsec and a width of height of 1 megaparsec. So that would be 12 and 1 instead of 10 and 1. So works pretty well. There is a beautiful paper by McCall on the local sheet that
okay. Okay, thank you.
Okay, we're hitting the end. Maybe I had one last question because I was to Luigi actually related. We were wondering about at like Mercurian 421 has been observed at 20 TeV, 30 TeV, and are there other like extreme blazars that are observed as such energies? I think you showed a plot in your talk where the deabsorbed spectrum increased rapidly or became hard. Jonathan or Luigi?
If you want.
Yes, in my slides.
But I suspect I have two. I have the plots that we. So what I would, okay, the source that we often use for LIV constraints, for example, is actually Mercurian 501, that we use a lot because it's been observed up to 20 TeV. And then 1ESO229, it's been observed also. I have 14 TeV in mind, but Luigi, you will correct me if I'm wrong for the highest energy point. Although this highest energy point has a pretty big uncertainty.
Yes,
so it depends whether you consider that 2 sigma, 3 sigma, or 4 sigma is an observation.
Yes, I would say it reached 10 TeV. The other point at 15 really depends on how you integrate that beam number of counts. Really, it's a bit delicate, let's say. But I was referring actually the plot that I showed. I think it was Mercurian 501. Yeah, the last 2 or 3 points of the Hygge spectrum that with the latest at least estimates of the infrared light, I think around between 10 and 20 micron. That is the region was just a slight upturn of the model of the EBL turns out in a strong increase of the optical depth, and so if you deabsorb a sort of upturn in the spectrum, and this I think is still a quite open question, and but I was wondering why. So far,
I'm sorry to interject. This is a problem solved, but I spent actually in 2015. It was a nightmare. The spectrum. I started with the IGRA spectrum from the analysis, the paper in 1997, and so for the story, I was a postdoc at UCSC at that time, and I analyzed the spectrum, willing to test both the EBL and LIV, and I ended up was an LIV signal. So I stayed at home. I told David Williams, look, I think I have something. I have to write down. I have to finish the analysis. We discussed it. And then we realized, as you said, Luigi, that there was a real analysis in 1999 of this very same spectrum with an updated calibration. And there, the LIV signal completely disappeared. And actually, the upturn, it's pretty consistent. So the upturn that you could infer if you overcorrected for absorption is not inconsistent with galaxy counts. And this is something that I discussed in the 2015 paper that we did with David. And I also showed
no, that's right. I was just referring, I think, to the latest, I think of one year ago, something like that, of an estimate of the EBL there, not from galaxy counts, but a bit more, that was just slightly higher. And that slightly higher would make the upturn still visible. And that I was wondering, let's say, what is the status of the analysis there? Maybe I think I've put it in my slides, but I don't remember exactly.
Do you want me to stop sharing?
I have to.
One thing that I can tell you. Yeah, one thing that I can tell you as far as galaxy counts are concerned, the points that you see here are the points from the gamma team, which I tend to give a lot of credit to. So these are the gray circles that are here. And
Okay, yes.
The model that is there in black is the model from Gilmore 2012. You can see that it fits pretty well, even if the points were obtained afterwards.
I was talking about, yes, the point, I mean, just only the point at 20-something micron. The one that is, there is a recent estimate of not of galaxy counts, but of the EBL, which is slightly higher. And if you put it, if you put it that slightly higher, and you try to modify the entire EBL model so to pass through that point, then it causes this kind of upturn, which comes back visible in the old Higgs spectrum. But I mean, from my impression is that it is still overestimated in some way. So the real count, I mean, the real flux is exactly what you indicated here, basically. But I was curious if, let's say, if there are other analyses or other measurements specifically in that region between 20 and 30 micron. And if there are TV spectra that reaches above 15-20 TV from the Markarian, because so far I've not seen many. I mean, they are all. I mean, the sources have not collaborated, let's say, to have a harder spectrum at a higher flux so that we can reach 25 TeV, the two Markarians. So probably we have to wait CTA to expand a bit, even just a factor of 2 in the energy range there.
Jonathan, can I ask you quickly about slide 17? I mean, I guess our session is over, but we are just
Okay, thanks, everybody.
17. So you had a comparison of the magnetic fields. I forget which slide that was. The nanogauss levels, maybe it was the one before this or the one after. Yeah, well, I don't remember now, but you were comparing different techniques. Oh, well, this one actually. So 17, yes. So what's the point here that you can, for these voids, you have two different sorts of limits, less than 1 nanogauss and picogauss?
No, sorry, that was maybe not clear the way I wrote it or the way I said it. Let's put it that way. Often cases, the goal of people playing with such simulations consists in trying to reproduce the magnetic fields in the densest regions that we know in the universe. So typically in the Coma cluster, where we have inference of the magnetic field profile from Faraday rotation. So we have quasars behind, and then we can see how much Faraday rotation there is. There are 7 of these quasars, and from this you can try to infer the profile of the magnetic field and its strengths, and it's reconstructed in the core of Coma at 5 microgauss typically. This is a paper from Bonafede 2010. Now, that being said, these magnetic field in clusters, you need to generate them, and there are multiple scenarios that are discussed, but often cases seed fields are welcome so that they can then be amplified and grow into the magnetic fields that are inferred in filaments or clusters. And 2 main scenarios are discussed: either a primordial origin, so that would be before CMB emission, and people often need a first order phase transition to generate such a magnetic field. And then they discuss QCD, electroweak, or inflation. And then they often fight about whether it's first order or not first order to see if they can generate their magnetic field. When you have such...
What? Sorry.
No, you okay, you want to interrupt me because
no, I'm going to go. I'm sorry for interrupting. Thank you again for a great talk. And I have
no
to
problem.
take care of a kid.
So when you start with such a primordial magnetic field, then you will tend to feel the entire volume of the universe. That's why we have this this green filling area everywhere. While if the seeds are coming from outflows of galaxies or active galaxies, then mostly what will happen is that the magnetic field will be located near the filaments and near the clusters. And so we have nothing basically in the voids. Not exactly nothing, because we started from a denser universe when the first structures formed, but still a pretty weak magnetic field. Here, typically less than a picogauss. Yeah. And so this is what I was alluding at here, is that likely this is the regime that we can probe with CTA. The very strong magnetic field case is something that would completely dilute our secondary signal. So there would be practically no hope to see any secondary, any signature for us.
Okay. All right, thank you. Thank you very much. I think we should just end the session. Thanks for everyone for staying. And thanks, Jonathan, for really an excellent summary. And please send me your slides so that we can post them. Thank you.
Thank you. Bye-bye.
Okay, see you in 2 weeks. Bye-bye.